Let's graph this piecewise function by first determining where that boundary wall is going to be, that invisible break in my graph. So it looks like -2 is where something special will be happening. So the very first thing I'm going to do is on my graph, I'm going to go on and add a dashed line when x is equal to -2. Something special should happen at my graph at that point. Okay, let's go ahead and then take a look at the first piece of this piecewise function. The first piece, we'll just call the top piece, is this x plus 3. And so what I'm going to do, like we did in the previous video when we were just graphing one of these at a time, is I'm going to use an xy table. Even though I can use ideas of slope-intercept form, sometimes the xy table is the best bet to start with these. So I'm going to begin my xy table with including that special boundary value. So I'm going to include -2 in my table, but then I'm going to make a note of whether I can or cannot actually have a point there. This time it says for this top piece, x has to be less than -2. So I can't actually have a point on the graph, and I'm just going to make a note in my table that I have an open circle when I get to that point. And then I need to pick at least 2 more values for x so I can graph this line, and it says I have to pick values of x that are less than 2. So values like, I don't know, -3 and -4 would be great. Okay, anything less than -2. From here, I'm going to take those values one at a time and plug them into x into the equation they gave me. You can do this on a calculator, but I think it's easier just to do it in your head. So -2 plus 3 gets me an output of 1. -3 plus 3 gets me 0. And then -4 plus 3 gets me -1. And so I have 3 values to now graph to plot this part of my function. So my first value was -2, 1. So I count backwards 2 spaces and up 1. And notice I'm on the wall. And so we made a note of whether we could or could not actually have a point there. And we said we couldn't, so I'm going to have an open circle. Make that really big so I can see that it's an open circle. My next point was -3, 0. That's just the point of the line, so it can be small. And then -4, -1 is a point down there, and I can keep using my slope, if I can get my point where I want it to be, there we go. I can keep using the slope to find more points, but I think I have enough to kind of sketch that in there. And so there's parts of my piecewise function, that ray right there. Okay, let me switch colors and we're going to move on to the other piece of this. The other piece of this function is this part of the line right here, -2x minus 3. So once again, I'm going to make an xy table. And I'm going to include that special boundary level to start with. So I'm going to include -2 and make a note of it this time that I can be equal to -2 this time. So I'll have a filled in circle when I plot this point. And then I have to pick 2 numbers that are bigger than -2, or at least 2 numbers bigger than -2. So how about -1 and 0? That would be great. Any 2 values are fine. All right, so again, let's one at a time plug those values in for the x down here this time and find out what my output is. So -2 times -2 is 4, and I subtract 3 and end up with a point of -2, 1. Notice they're the same point this time. That's a total coincidence. It does not always happen that way. Plugging in the other x values, you can pause the video, or maybe you've already done it or can figure it out real quick in your head. But there's my other 2 output values. So let's plot these 3 points and see what the other part of this piecewise function looks like. So applying the point -2, oh look, I'm on the wall. Up 1, oh, I've just said I have a filled-in circle. Total coincidence that these points are at the same location. So this time, actually that hole we had in the graph ends up getting filled. So there is no hole in the graph this time. I have a point everywhere. My next point was -1, -1. So right down here. And then my third point was 0, -3. And again, you can use ideas of slope and slope-intercept form, but it doesn't always work. You have to be kind of careful with these boundary lines. I can draw this other part of my graph in there, and then there we go. There is our piecewise defined function. It's made up of 2 different functions. Kind of looks like an absolute value graph, but a little lopsided. These bottom 2 questions, real quick, we can answer those. Is the domain all reals? In other words, no matter where I go on the x-axis, whether I go left or right, is there a graph above or below me? Can I get an output for every input I plug in? The answer is yes. There's no breaks. There's no gaps in the graph. And then the next question is is the function continuous? Means could you draw this without picking your pencil up off the paper? Basically is what it means. And the answer this time is yeah. You can draw this just fine without picking up your pencil.